One of the really important things you will do and use throughout your course is writing net ionic equations for reactions carried out in aqueous solutions. The process of writing net ionic equations combines a lot of concepts. So to avoid mixing together too many concepts at once, I would like to break the process into 3 pieces. This video will deal with one piece, converting the formulas of the substances from the form in the regular equation, called a full formula equation, into the form that will be used in what has been called a complete ionic equation. Part 2 will be writing that information as balanced, complete, and net ionic equations. The other part will deal with writing the products when all we know is the reactants. The reactions we will be talking about here include precipitation reactions, acid-base reactions, gas-forming reactions, and oxidation-reduction reactions. They might be the double replacement type or single replacement type or other types, but they are all carried out in water. My goal is to look at everything together, to work towards creating a system to always get the right answer, even for hard problems, with the least amount of fuss. Sound good? You may have already figured out a way to do this yourself. Here's mine. First, some background. Here you see the 3 types of equations that we typically talk about in the context of net ionic equations: the full formula equation, the complete ionic equation, and the net ionic equation. The full formula equation is a reaction equation written in the usual way. The full formula of each substance is shown. The complete ionic equation shows the predominant form that each substance has when it is in water. For some substances, that form is ions, but definitely not for all substances. So I really don't like the term complete ionic equation, which is what's used in most textbooks, because it makes you think that you should put everything into ion form, and you shouldn't. A guaranteed to be confusing term. So, I have given these reactions a new name: reality equations. You heard it here first. Perhaps major reality would be better, since it shows the form that is the major form in water, if more than one form is present. The net ionic equation shows only the changes in substances that occurred from reactants to products during the reaction. This is usually derived from the complete ionic, or reality, equation. In the reaction shown here, you see that the change is that lead-2 ion and bromide ion were free ions in solution in the reactant mixture, the left side, but are stuck together into PbBr2 in the product. The H+ and nitrate ions didn't change, so are left out of the net ionic equation. Here is my general system for determining what form predominantly exists in water for every substance in every kind of reaction. In other words, how to decide the form of the substance to write in the complete ionic, or reality, equation. A copy of this slide is available. There are certain things you will have to memorize: the 3 compounds listed in item 1, the 6 common strong acids, and the ionic compound solubility rules, or you may have to know how to use a table provided by your professor. A simplified table is available with this video. You will also need to remember that ionic compounds are compounds whose formulas contain a metal ion or NH4+, and one or more nonmetals. And of course, you need to know the charges and formulas of ions, including polyatomic ions. We'll start with the first rule: compounds that decompose in water. It is important that you evaluate this first because these substances could also be evaluated by the other two rules, which would then give the wrong answer. This is the category most missed by students. These three substances, ammonium hydroxide, carbonic acid, and sulfurous acid, decompose in water to give mostly molecules of water and a gas. Let's look at NH4OH. Watch the structure in the beaker carefully to see what happens in water. When NH4OH is formed in a reaction, most of it becomes NH3, ammonia gas, and water, liquid. Although some of the NH4OH, ammonium hydroxide, stays as ions, which accounts for the fact that its aqueous solutions are basic, some of the gas may escape from the solution, so you will smell the ammonia. Some books will list the NH3 gas as NH3 aqueous, since it is also soluble in water. There is no solid compound with the formula NH4OH. When NH4OH is listed as a reactant, it is really a solution of NH3 in water. In fact, lab reagent bottles are sometimes labeled as NH4OH and sometimes labeled as NH3 aqueous. The substance is the same. So write NH4OH as NH3 plus H2O in the complete ionic or reality equation, whether it is written as a reactant or as a product. The other two substances follow the same principle. Watch the structures in the beakers carefully. And with these, also you will write the gas plus water form in the reality equation, whether the substance is in the reactant side of the reaction equation or the product side. If the substance is a product, you are more likely to see bubbles form when you have CO2 or SO2 than when you generate ammonia, because carbon dioxide and sulfur dioxide are less soluble in water than ammonia. Acids, ionic compounds, and everything else. Here are rules 2 and 3. Rule 2 lists the substances that should be written as ions: strong acids and ionic compounds which are soluble in water. Not all ionic compounds, just the ones that are soluble in water. We know that these things ionize in water because their solutions strongly conduct electricity, making a light bulb light in a conductivity apparatus. Strong acids are defined as those acids that essentially completely ionize in water. There are only 6 common ones, so we memorize those and consider any other acid to be weak and therefore not written as ions. Ionic compounds that dissolve in water do so because the polar water molecules surround each ion with an attraction large enough to overcome the ion's attractions to its oppositely charged ion. So whenever an ionic compound has dissolved in water, it has had its ions separated. Rule 3 says that everything else is written as it was in the original equation. That means that you don't add charges or change anything. Everything else will include things like weak acids, water-insoluble ionic compounds, and things that aren't acids or ionic compounds at all, like solid metals and other elemental substances, or organic or other covalent substances. Here is a simplified solubility table that we will use for our exercises. It is available as a handout. It may be a little different from the one provided by your professor because to keep the table reasonably small and comprehensible, only the common compounds are included. Opinions about how detailed the table should be and what compounds will be commonly encountered will vary. Compounds are also actually not just soluble or insoluble, they vary in the number of grams that can dissolve in a given volume of water. There is therefore sometimes a difference of opinion as to how to classify the few that are not clearly soluble or insoluble. In addition, some decompose in water, so there's a difference of opinion as to how to classify them. If the compound has any of the ions listed in the top group, it is water soluble, except for the exceptions, of course. And we love those exceptions, don't we? So anything with potassium, sodium, lithium, or ammonium as the plus ion is water soluble. Anything with nitrate or acetate ion is water soluble. If it has chloride, bromide, iodide, or sulfate, solubility depends on what other ions are present. For example, iron 2 sulfate is soluble. Barium sulfate is not soluble. If the compound contains negative ions in the bottom group, it is insoluble, unless it also has one of the positive ions from the top group, the solubilizing ions list, such as sodium, potassium, lithium, or ammonium, or unless it's one of the exceptions mentioned. So sodium sulfide would be soluble, even though other elements, sulfides, would not. Let's do some examples. Here are a few examples. The rules are included at the top of the page for your reference. How should we write the formula for the substances in the beakers to make them be the right form for the complete ionic or reality equation? In other words, what is the major form of the compound when there is water in the beaker? Pause the movie and formulate your answers. Okay, lead 2 nitrate, the first one. Let's see what happens when we put water into the beaker. Watch the beaker. Why did it separate into ions? It's a soluble ionic compound. It has nitrate in it, and those are all soluble. Since it separates into 1 lead and 2 nitrate ions, we would write it as Pb2 plus 2 NO3 minus. Note, when writing ions, you must include the ion charge, so that means you must remember the charges on ions, including the polyatomic ions. Okay, now lead 2 bromide. Watch the beaker. What happened? Nothing. Why? Bromides are insoluble if they also have lead in them. So this should be written as is, not as ions. And be sure you don't show any charges. Just write it as it was. Do you know what to do with lead? Nothing. Remember that these solubility rules are for ionic compounds, and that ionic compounds are compounds whose formula contain a metal ion or ammonium and 1 or more nonmetals. You never use the solubility rules to determine the form for an element. It is an everything else. Just write it as is and no charges. Let's try some more examples. Pause the movie if you want some time to figure them out. Okay, first one, calcium chloride. Watch the beaker. Why did it ionize? Chlorides are soluble unless they have lead, silver, or mercury 1 ions, and calcium is not one of those exceptions, so it's soluble. We therefore write it as Ca2 plus 2 Cl minus. Now, some of you may have been tempted to write Cl2 2-. You do not want to do that. You want to indicate that you have two of the Cl- ions, not one ion with two Cl's stuck together with a 2- overall charge. So we always have the 2 in front. That means two of. So we'll get rid of that comment there. Okay, ammonium phosphate. This one has 3 ammonium ions. It has ions both in the soluble and the insoluble category. Remember that if a compound contains any ion that makes the compound soluble, the whole compound is soluble. So this one is soluble and written as ions 3NH4 plus PO4 3-. Don't forget the charges. Mercury 1 nitrate. Watch the beaker. Why? We have nitrates, so it's soluble. Are you wondering about that Hg2 2+? I just told you that we do 2 of the Cl minuses, 2 Cl minus, not Cl2 2-. Why don't we write 2 Hg plus 1s here? Well, it turns out that this is an unusual circumstance, called an exception, because the 2 mercury atoms in this ion like to stay bound to each other. There are very few ions like this. The only other common one we will see is peroxide, which is O2 2-, as in sodium peroxide, Na2O2, or hydrogen peroxide, H2O2. Just remember for now that the mercury 1 ion always has the formula Hg2 2+, 2 mercury 1 stuck together. Here are some more examples. Pause the video to think about them. Hint: these are not ionic compounds. Because they contain all non-metal atoms, H is a non-metal, no metal ions, no NH4+, these are not ionic compounds. They are acetic acid. How would that be written? Without ions, as is. Although it has some ions in solution, it is a weak acid. It is only ionized a little bit. It is a weak electrolyte. So ions are not its major form, and it is not written as ions, whether it is a reactant or a product in the reaction. Try HBr. Okay, HBr is written as H plus and Br minus. Why? Well, it's a strong acid, and strong acids are completely ionized in water. Water. We just write it as H2O. It is not a strong acid. It is not an ionic compound. It is an everything else. How you doing? Okay, now for a quick review. When you finish, you might try the additional questions available as a handout. For the quick review, I will fill in compounds in the top 3 left beakers, then the answers below, then the 3 right beakers, and then the answers below them. See if you can guess the answers before they appear. This is a challenge. Have fun.